Hello students, we are studying metric spaces. As you know, in the definition of a metric, we have considered the concept of distance of one point from the another point. Now we are going to study two more concepts. The first one concept is the distance between two non-empty sets, and the second is the distance from a point to a non-empty set. The non-empty set simply called as set. Okay. So we'll begin with the first concept, and it is the distance between two non-empty sets. So number first is distance between two non-empty sets. We'll define the distance between two non-empty sets. Let X be a metric space. Let X be a metric space and A, B be any two non-empty subsets of the metric space X. Let A and B be any two non-empty subsets of the metric space X. Then the distance between sets A and B, distance between the sets A and B is denoted by d of A, B, and it is defined as so definition of the distance between two non-empty sets is distance between sets A and B is equal to the infimum of the set of distance between points A and B, where A is a point in the set A and B is a point from the set B. Okay, so like such, the distance between sets A and B is defined. I will explain this by drawing a diagram, and this is just for the understanding purpose. So let us consider two sets A and B. Suppose we have the first set A, which is this. Suppose this is the set A, and suppose it consists of 4 points. P, second is suppose Q, third one is suppose R, and fourth one is suppose S. P, Q, R, S. And let us suppose that there is another set, and that set is, I am drawing here. Suppose this set has 3 elements, and the elements of this set are X, Y, and Z. Let us suppose that the first set is A and the second set is B. Then, to find the distance between A and B, obviously we have to find out the distance of each point of set A from each point of set B. Distance of point P from the point X I am showing by this blue colored line. Next, distance of P from the point Y, it is shown here. Distance of point P from the point Z is shown here. So we have considered distance of point P from each and every point of the set B. Next, we will consider the distance of point Q from each point of set B. So first of all, distance of Q from the point X. is such. Next, distance of Q from the point Y. I am drawing here. Next, distance of Q from the point Z. I am showing here. Now next one, distance of point R from the point X is as such. Next, distance of point R from point Y. I am shown here. Next one, distance of R from the point Z is this. Next, distance of point S from the set X is this. Next, distance of point S from the point Y is this. And finally, distance of point S from the point Z is this. So likewise, we find out all such distances. So we have found out the distance of each point of A from the distance of each point of B. And of all such distances, we have to consider the infimum, the smallest distance. Okay? And that the infimum of that set of distances will be the distance between sets A and B. So, we have to consider all such distances. So, in this particular example, there are 12 distances. And the distances are distance of P from X, then distance of P from Y, distance of P from Z, next distance of Q from X, distance of Q from Y, distance of Q from Z, distance of R from X, distance of R from Y, distance of R from Z. Next, distance of S from X, distance of S from Y, and distance of S from Z. Okay. So, of all such distances, whichever is the infimum. So, of all such distances, whichever is infimum, it is our distance between sets A and B. So, like such, we have defined the distance between two sets. Later on, we will consider some more examples about the distance between two sets. So, after this first concept of the distance between two non-empty sets, next we will move to the second concept, and that second concept is the distance from a point to a set. Now we will define the distance of a point from a set. Distance of a point from a set. Distance of a point from a set. We will define this one. Obviously, set means here also it is non-empty set. So the definition is, let X be a metric space. Let X be a metric space. Capital A be any non-empty subset of X. Any non-empty subset of X, and small x is any point. Small x is any point in the metric space capital X. As small x is any point in the set capital X, which means that it may be a member of A or it may not be a member of A. Both the possibilities are open. Okay. Then the distance of point X, then the distance of point X from the set capital A is denoted by. So it is denoted by the notation d of X comma A. Here X is small as it is a point in the metric space. Okay, and it is defined as. How it is defined? So it is defined as d of x comma a is equal to the infimum of the set of distances of point x from the point A, where A ranges over set A, means A is a point of set A. Like such, distance of a point from a set is defined. We'll consider one example so as to understand this properly. Let we have a set. This is suppose set A. Suppose it consists of three elements P, Q and R. And suppose we have a point. That point is suppose x. Then to find the distance of point x from the set A, we have to consider the distance of point x from each and every point of the set A. Therefore, we will find out the distance of point x from the point P. We will find out the distance of point Q from the point x and distance of point R from the point x. Of all such distances, whichever is infimum, that infimum of this set is called as the distance of point x from the set A. So in this way, we have defined the distance of a point from a set. Now let us consider some more examples for the understanding purpose. So consider some examples. If A is equal to, we will consider the set A. So A is the set of all x belongs to R, means it is a set of all real numbers such that 0 is less than x is less than equal to 1. Means capital A is the semi-open interval 0 to 1. It is open from the left side, means from the 0 side, and it is closed from the right side, means from the 1 side. Okay, and D is the usual metric. If D is the usual metric, we have studied the usual metric already. Okay, then we'll consider distance of point 0 from the set A. Okay, then the distance of 0 from A we'll consider, and for that purpose I am drawing a diagram. So let us consider a diagram. Suppose this is the real line. On this real line we have 0 here. Suppose here it is minus 1, and suppose this is 1. Then the set A is nothing but, here the set A consists of all the points which are greater than 0 and less than equal to 1. So that I am indicating by the green colored line. So this is set A. It consists of all the points which are greater than 0. So therefore this is not touching the line of 0. And it consists of all the points up to 1. Okay. So here A is equal to, it is the semi-open interval 0 to 1. Clearly 0 is not a member of set A. Okay. But if you find out the distance of 0 from the set A, then distance of 0 from 1 is obviously 1. Distance of 0 from 0.8 is 0.8. Distance of 0 from 0.65 is 0.65. Distance of 0 from 0.4 is 0.4. Distance of 0 from 0.1 is 0.1. Distance of 0 from 0.0001 is 0.0001, and so on. And all these are members of the set A. And of all such distances, the infimum of such set is obviously 0. So here in this case, distance of 0 from the set A is 0. Okay, even though 0 is not a member of the set A. So even though 0 is not a member of set A, and obviously if you consider a member of the set A, for example if you consider 0.4, then 0.4 is a member of the set A, and distance of 0.4 from the set A will be obviously 0, as the distance of 0.4 from 0.4 will be 0. And therefore, from this it is also clear that if x is a point of the set A, then distance of x from set A is equal to 0. Okay? If x is a member of set A, then the distance of x from the set A is 0. Next one. But however, distance of x from A equal to 0, this doesn't imply that x belongs to A. Okay? If x belongs to A, then it implies that distance of x from A is 0, but its converse is not true, which means that if distance of x from A is 0, then it doesn't imply that x belongs to A, as it is clear from the example which I have discussed just now. Okay, so from this example it is clear. Next one, we'll consider the next example. Next example is, let A equal to, let A is the set closed interval -2 to 1. B be the set, it is semi-open interval 0 to 3. Next, let C be the set, it is semi-open interval 3 to 5. And D is the set, it is semi-open interval 5 to 8. Okay, then we'll find out the distances between these sets A, B, C and D. We'll study this example by drawing the number line. Real line I am drawing here. Suppose here it is 0. To the left side of 0 is -1, -2 and beyond. To the right side of 0 we have 1, 2, 3, 4, 5, 6, 7, 8, 9 and so on. Now first of all we will consider the set A. Set A is the closed interval -2 to 1 that I am showing by the green colored line. Okay, set A is the set closed interval -2 to 1, -2 to 1, which means that as it is a closed interval, it means that it consists of all the points lying between -2 and 1, and it also includes both endpoints -2 as well as 1. So this is our set A. Next one, set B is the semi-open interval 0 to 3. It is open from the right side, which means that 3 is not its a member, but 0 is its a member. So semi-open interval 0 to 3 means it is this set. Okay, and this set is our set B. Next one, set C is the semi-open interval 3 to 5. 3 to 5. Again, it is open from the right side, which means that 5 is not its a member, but 3 is its a member. And also, all the real numbers lying between 3 and 5 are its a members. And finally, the set D is semi-open interval 5 to 8. It is this. It is open from the left side, means from the point it is open from the left side, means it is from the side 5. So this is the, it is open from the left side, means it is open from the side 5. Okay, so this one is our set D. Like such, we have the sets A, B, C and D. Okay, so next one, if we consider the distance between sets A and B, then the distance between sets A and B is 0. Why it is so? Because if we consider sets A and B, then they have some points in common. So if two sets have common points, then definitely the distance between such sets will be always 0. For example, sets A and B have 0.3 as a common point. So therefore, the distance of 0.3 of set A from the 0.3 of set B will be obviously 0. Similarly, set A and B also have 1 as common point. Therefore, distance of point 1 of set A from the point 1 of set B will be 0. Actually here sets A and B have infinitely many points common. Okay. So if A and B have at least one point common, then definitely the distance between them will be always 0. But however, the distance between two sets is 0, then it doesn't mean that they have common point. Okay. That also we are going to discuss later on. So the distance between sets A and B here in this case is 0. Next one, if we consider the distance between sets A and C, then the distance the set A and the set C do not have any point in common, and it is clear that the distance between sets A and C is the distance between 1 and 3, which is obviously equal to 2. So distance between sets A and C is 2. Here we are considering the usual metric. Next one, the distance between sets A and D. Distance between sets A and D. It is again clear from this diagram that the distance between A and D is same as the distance between points 1 and 5, which is 4. Next one, the distance between sets B and C. Distance between sets B and C. Now here B and C do not have any point in common. Okay, sets B and C are disjoint. They do not have any point in common, even though the distance between them is 0. Why? Because if you consider the point 2.999 of the set B and the point 3 of the set C, then the distance between them is 0.001. But set B also have points such as 2.999999999. Then the distance of that point from the set C will be still less. And like such, there are so many points in the set B. So therefore, infimum of all such distances will be certainly 0. Therefore, distance between B and C is 0, even though B and C are disjoint sets, means they do not have point in common. Okay. Next one, if we consider the distance of set B from the set D, then obviously it will be equal to the 2. Next one, if we consider the distance of set C from the set D, then it is equal to again 0. Okay. Here again sets C and D are disjoint. They do not have any point in common, even though the distance between them is 0. Next one, again we will consider the distance of point from set. So if we consider the distance of 1 from the set A, then 1 is a member of set A, therefore distance of point 1 from set A is 0. Next one, if we consider the distance of point 2 from the set A, then 2 is not a member of set A, and therefore here in this case it is clear from this diagram that distance of point 2 from the set A, it is equal to 1. Next one, distance of point 3 from the set B, if we consider, then from diagram it is clear that 3 is not a member of the set B, even though the distance of 3 from the set B in this case is 0. Okay. So like such we can consider so many distances. Next one. So from all this discussion, it is clear that we have some important points to note. Okay. So from all this discussion, it is clear that what it is clear. Number first, if x belongs to A, means if x is a point of set A, then this implies that distance of x from set A is equal to 0. Next, number second, if distance of x from set A is equal to 0, then this doesn't imply that X belongs to A, which is clear from the earlier example that was discussed just now. Next one, number 3, is if A intersection B is non-empty. Means if A and B have at least one point in common, okay, then this implies that distance between A and B, distance between sets A and B is certainly 0. But however, its converse is not true, which means that if distance between sets A and B is 0, then however, it doesn't imply that A intersection B is non-empty. Okay, so even though A intersection B is empty, we may have the distance between them as 0, which is clear from the example that we have discussed just now, as sets C and D were disjoint. They do not have any point in common, but the distance between sets C and D was equal to 0. Okay, so these are some important points that we have mentioned here. Now next one, we will consider one more example here, and it is the example number 7. Example number 7. Let X is equal to, X is the set having members 1, 1 by 2, 1 by 3, 1 by 4, and so on, 1 by n, and continued. Means here the capital X is the set of reciprocals of all natural numbers. Okay, and suppose that D is the usual metric. D is the usual metric on the set X. Usual metric on the set X. Okay. Again, let capital A be the set which consists of the reciprocals of odd positive integers. Means capital A is equal to 1, 1 by 3, 1 by 5, 1 by 7, and so on. Nth member in this set will be obviously 1 upon 2n minus 1. So, like such, we have the set A, and let us suppose that B is the set which consists of the reciprocals of even natural numbers. Means B has members 1 by 2, 1 by 4, 1 by 6, 1 by 8, and continued. The nth member will be 1 upon 2n, and again continue. Okay, so here we observe that A and B both are subsets of the metric space X, and they are such that they do not have any point in common. Okay, so here A intersection B, it is equal to 5. A and B do not have any point in common, so A intersection B equal to 5. But we have the distance between sets A and B as it is equal to 0. Why it is 0? Because if we consider the distances, then the distance between 1 from 1 by 2 is 1 by 2. Distance of 1 from 1 by 4 is 1 by 4, and so on. If you consider all such distances, then as we go towards the right side, then the distance between the corresponding points will be very, very small, and it will tend towards 0. Therefore, the infimum of all such distances will be certainly 0, and therefore the distance between sets A and B is 0, even though they are disjoint sets. Okay, this is in support of the fourth note that we have mentioned here, that if A intersection B is empty, even though we may have the distance between them at 0. Okay, so in this manner, in today's class we have discussed two important concepts. The first one was the distance between two non-empty sets, and the second was the distance from a point to a set. and we have also discussed some examples. Today we will stop here and we will continue in the next class. Thank you.